Alright everyone, let's look at an example where we have to determine the direction of the induced current by changing the magnetic flux. So, if we have a long straight wire carrying a current surrounded by 4 loops, if the loops are dragged in the direction of the velocity vectors as shown, what will be the directions of the induced currents in each of the loops, A, B, C, and D, if any induced current at all? So, when we're faced with a problem like this, the type of answer we're looking for is if the induced current is clockwise or counterclockwise. So let's start at loop A down here. And if the loop is moved in the direction of this velocity vector, it is going to be repositioned like this. Okay, so this is loop A. If it's repositioned like that, you can see by the magnetic field that I have drawn around this current carrying wire that we're going to an area where there's less magnetic field. So as we know from our formula, B is inversely proportional to R, the distance. So as we get further away from this current carrying wire, the magnetic field strength decreases, and that's kind of shown by how as we're further and further away from the wire, there's less and less dots. So when we move this loop A away from the wire, we're going to an area where B is less. So if B is decreasing, therefore the magnetic flux is decreasing. And remember, we always want to resist the change in flux. So if the flux is decreasing, we're going to want to increase the flux. So this is what we want. We want to increase the flux. And how can we do that? So whenever we want to increase the flux, we have to add some induced magnetic field to the already there magnetic field. So what does that mean? So the already magnetic field that is in this new position of loop A is coming out, which is noted by the dot. So to resist the decrease from how we have 5 dots over here, we're going to add some more, like that. So this is resisting the decrease if we're adding more magnetic field lines. So this is our B induced, okay? And from there, what you have to do is use your right-hand rule, where your fingers are the direction of the magnetic field, the induced magnetic field, and your thumb is going to be in the direction of the induced current. So in the new position of loop A, our fingers are pointing out towards us. And no matter how you orient your right hand, you can see that the direction of the induced current will be like this, right? So this is a counterclockwise. So for part A, I induced is counterclockwise. Okay, now let's look at part B. So if we have loop B and we move it like this in the direction of the velocity, we're moving it to an area where there's more magnetic field. And let's draw this out. So if we're increasing magnetic field, we're going to be increasing flux, and we want to resist that. So we're going to want to decrease the magnetic flux. And how do you do that? So to oppose the change in flux, we're going to add magnetic field in the opposite direction of the already there magnetic field. So this is B induced. Okay, and again, using your right hand rule, your fingers go into the page, and we can see that our thumb is going to wrap around like this. So for part B, I induced is clockwise. Okay, now let's look at part C. Let's redraw the new position of loop C like this. So we're going from an area with less magnetic field, only 3 x's in this loop, compared to this area of the new loop, loop C, where there are 6. So we went from low to high, okay? So we increase the magnetic field, therefore we increase the flux in the loop, and we want to oppose this, so we want to decrease flux. So how do we do that? We're going to have to add some magnetic field lines, some induced magnetic field in the opposite direction. So I'm going to add 3, just like that, to bring it back to how we started over here. Okay, and then from there, use your right hand rule. So using your right hand, your fingers are coming out towards us, and your thumb, no matter where it is pointing counterclockwise, like that. So for part C, loop C, I induced is counterclockwise, like that. Okay, and lastly, part D. Let's redraw what's happening here. So we have it in an area where it's close to the wire, there is a lot of magnetic field strength. And now we move it to an area just down, parallel to the wire. And as we can see, we have 1, 2, 3, 4, 5, and almost 6 magnetic field lines initially, and that's exactly what we end up with, almost 6. So we're not moving it a distance away from the wire, we're just moving it either up or down in the same magnetic field strength of the wire. And what that tells us that we're not changing the magnetic field strength, and therefore we're not changing the flux. So in that case, if there's no change, there's going to be no induced magnetic field and no induced current. So there's going to be no current through the new position of loop D. So no induced current. All right, thank you all for watching.